Hi there, everyone. Thank you very much for joining us today for our webinar on RF fundamentals. This is the final part of our three-part series, and it has had an overwhelming interest, so thank you very much for your attendance and participation. If you have any feedback or other webinar topic suggestions, then please let me know by chat, or you can email me later at marketing@testforce.com. Before we get started, I'd just like to let everyone know that this webinar will be recorded and you'll be receiving an email afterwards with the recording, so you can go ahead and share it with anyone you think would be interested or rewatch it if you'd like. If you're interested in any of the other webinars we'll be hosting, or to download any of the free resources we have available, such as white papers or application notes, please go ahead and visit testforce.com/academy, and you'll find everything you need right there. If during the webinar you have any questions, make sure that you ask them in the Q&A section in the right side menu bar, and we will be sure to get to all of those questions as we get to the end of the presentation. And now, without further ado, let's jump right in where we left off last month and talk about RF fundamentals with Neil Jarvis.
So we're going to talk now more about modulation. So, now we're going to put information on these signals that we've been talking about, and that's really why you care, right? So, talk about basic modulation, analog IQ, blah, blah, blah. And so this is kind of, how all this early stuff used to work. In fact, your AM, FM radio still work that way. I know there's digital radios and stuff, but the old radio in your car still works the same way. Okay, so a basic sine wave. So I'm going to beat you to death with sine waves. I already think I have, but so A sine or cosine 2 pi ft plus v. Okay, so A is the amplitude, F is the frequency, phi is the phase. So again, you look at it in the time domain, it's a nice little sine wave, and in the frequency domain, it's a perfect line of infinitely narrow width, which obviously isn't real, but zero bandwidth, and that's kind of our starting point. So what is modulation? So basically, we want to send information somehow from one place to another. And so we're going to put some perturbation on these characteristics of the sine wave to send it over some medium, and then we're going to take that information off and do whatever we want to do with it. So any reliable, detectable change in the signal characteristics. So again, it's typically amplitude, phase, or frequency, or a combination of those. So you'll actually see that we do QAM is an example of quadrature amplitude modulation. So that has a phase component and an amplitude modulation component to it. Okay, there's our good old sine wave. There's the amplitude, the frequency, and the phase. Okay, so if you look at it, the sine waves, so there's the unmodulated carrier. So a carrier is really the thing that carries the information, hence the name, right? Carrier. So it's not usually something that's changing. So an example, like when you put that LO in the mixer, you're going to have a higher frequency thing that may actually be the direct carrier, but it's some high frequency sine wave that has no information on it. Then you're going to take some information. So we're going to start out just talking about analog modulation because it's easier, but then it'll move towards digital modulation, which is obviously what everybody cares about today. So what am I going to do? So in this case, and sorry I can only point at one screen at a time. So anyway, so the unmodulated carrier, we're going to add this low frequency component to it. And what does it look like? So for an amplitude modulation, the third line, you see, basically you can see now that high frequency thing is getting smaller and bigger and smaller and bigger. So the change in that amplitude of the high frequency carrier is the information. Okay? So that's what we're going to transmit through whatever medium, using an antenna or whatever, and then take that off on the other side. So what does it look like in our good old spectrum analyzer? We make them. So basically, there's analog modulation. You see there's the carrier, and then you see these two sidebands, right? So the modulation, so this is basically that sine wave, the frequency of that sine wave. Oops, wrong way. So you'll see there, it gives you a plus and a minus. So that's 1%, 10%. So you can see here, as I'm increasing the AM, it's getting closer and closer to the amplitude of the carrier. Okay? So that was amplitude modulation. So now we're talking frequency modulation. Take that same carrier, same information signal, and now instead of changing the amplitude of the carrier, I'm changing the frequency. So you see here, as the amplitude increases, the frequency gets faster. So the information is on the change in the frequency. Okay, so level of modulation, they call it beta. It's a change in F over F sub m. And when you look at it, similarly, it gets wider, you'll see in frequency as I increase. So instead of the amplitude of those tones going up, I get a wider bandwidth and more tones. That makes sense. Okay. Question?
For FM, why do you get more tones as opposed to just getting a wider band?
Think about that. It's a good question. So I'm.
The frequency is very continuous.
Yeah, but you're getting more frequency components, right? So as you see that amplitude gets bigger, you're going to have a yet even higher frequency. The highest frequency component will be right here, right? And as this amplitude's getting smaller, it has a lower frequency component. So as your amplitude gets bigger, you're going to have yet more frequency content.
Why it's really wide.
Wide, yeah.
Why isn't it continuous?
Question.
Or is it just this particular implementation is digital?
No, this is not a digital. Yeah, I think it's a sampling thing. Yeah, I'm not. That's a good question. I don't know the answer to that. Yeah. Yeah, I mean, I know, so that modulation index, so that's really my information source. So at 10%, you know, I can't even read the scale on that. That's AM, sorry. Beta is delta F over F sum M. Yeah, I'll have to think about that. It's a good question. Yeah, I don't know the answer to that. It's a great question. You stumped me. Okay. So we talked about AM and FM, and then you can change the phase, right? So remember we had the A sine cosine 2 pi ft plus phi. So phi is the other thing that we can modify. And typically phi is done more in a discrete manner. So you'll see here, you typically don't do like a linear phase change. You would do discrete points, kind of to your point. But it would be, you know, usually it's a 180-degree phase shift or a 90-degree or something like that. So that's more often what you see. But then in the end, you're going to do a combination of them, right? You're going to do typically amplitude and phase. So all pretty much digital modulation stuff that you see now is a combination of amplitude and phase modulation. So whether it's 802.11 or LTE or whatever, they mostly, if you underlying into what's the modulation, it's QAM. Okay? So what are some of the advantages, disadvantages? The advantage of AM, it's really easy to design it. AM radio stations, obviously they were cheap. That's why they liked them in the beginning. Really simple. You're varying the amplitude, frequency. It has the best noise immunity because typically more of the noise that you're going to see in the real world is going to be amplitude noise. Has the best SNR. And you don't need a really linear amplifier. Okay? Because obviously if you have, in this case, if the amplifier is not really linear, when you put signals in to amplify them, they're not going to necessarily amplify in a perfectly linear fashion, so you're going to get distortions. Okay? And then phase has very similar characteristics to FM. And pretty much everything digital has PM in it. Okay, so we're going to talk about I and Q. So basically, how do we typically organize this so that we can transmit that information? Okay, so moving down here. So amplitude and phase on a phasor diagram, right? So we talked about a vector phasor, so this thing now has an amplitude, the length of it, and a phase, right? So if we downconvert a receiver to baseband, we're taking out the carrier. We talked about the carrier. And then you're going to plot the sine wave as a vector. And the phase component is that rotation, and then the amplitude is the amplitude. Obviously, you could look at this in an XY fashion, but this is typically done as a phasor because it's easier to demodulate. The circuitry is easier. Again, our friend, the sine function. Okay, so if you look at the analog modulation, what does it look like in that vector phasor diagram? So I have a vector. So AM, basically I'm changing the length of that vector, right? The information is put on the length change. The phase modulation is a rotation of that relative to some starting point where the carrier is. Frequency, again, is a rotational thing. And then QAM is really a combination of the two. Okay. So we're going to start out with what we call a quadrature signal. So transforming our signal model to I and Q components. So basically, we have some sine wave, right, which is a vector. You can look up in a table to take these identities, and we basically can get, what is the horizontal component or x component, what's the y component. But how do I design this, right, to make that vector? So that x vector has an x component and a y component. So it's actually, this is a really simple circuit. It's a really inexpensive, simple circuit to make. That's why they use it for everything. Is basically, you have two mixers and then a phase delay between them. So when these things combine, these things are going to come out with a phase difference of 90 degrees between the two, and then they get combined. So basically now you are taking in, a bit stream, and there's some bit mapping that goes on somewhere else where you're taking a bit stream and you're going to split it out into two paths. That's beyond the scope of what I'm going to talk about because I'm not a digital guy. But basically, you're halving the bit rate by doing that. Okay? So the data or information is coded into IQ and then modulated onto a carrier. So basically, that IQ stream is now going to go with the carrier. The carrier is mixing it up directly, right? So this carrier is feeding both of these mixers at the same time, the same carrier, the only difference being that this one is 90 degrees out of phase from that one. So then the resulting RF signals, you're going to combine them, okay? And they won't interfere because they're in quadrature. So the resulting, there's an IQ, it's commonly referred to as complex baseband. So basically, if I have a bit stream, I'm going to want to split it out into an I and a Q. So again, halving the bit rate. And you'll often see that I plus JQ. No, nothing that interesting there. But again,
the I and the Q signal will go into the summing node, right?
Yeah, they go. So basically, this summing node, there's an I. So there's a baseband I, which really isn't anything to do with whether it's in quadrature. It's just the data bit stream has been split, right? So depending on how you do that, the mapping. But you could say, like, if you had 1, 0, 1, 1, you could take 1 goes to I, 0 goes to Q, 1 goes to I. So you're now half the bit rate, right? But they don't necessarily go every other, right? So then you're just summing those in RF.
But the node at the top should be I. The node at the bottom is Q.
Yeah, but they actually come out. They're at the same frequency. If you look on the spectrum, you're going to see that carrier with some bandwidth associated with it. Okay, and again, we like these because they're easy and cheap, right? Question?
Is there a reason for calling I?
Well, I is in phase, Q is quadrature, you know. Yeah, 90 degrees, yeah. I don't know who decided that originally, but. So, you know, the IQ modulator, it enables simultaneous amplitude and phase modulation. So I'm doing amplitude and phase together, right? So in the simplest case, if I'm doing BPSK or QPSK, there's no amplitude component, but then I can add an amplitude component very easily. Okay. So how could we use this to create a fixed signal? So i.e. just a carrier. This is somewhat uninteresting, but you have a vector which is fixed in time. So this is showing, you know, the I and the Q, but it's constant. So it's going to give you some point which is just a fixed vector. So if you looked at that, it wouldn't move, it wouldn't rotate or anything like that. So these are different things you could have if you had an I but no Q, or if you had a Q but no I. That's what these are. Or if you had an equal, you know, I and Q component. Okay. What if you want to use an IQ to create a fixed frequency at an offset? It traces out a circle. Again, these vectors basically rotate, right, as a function of frequency. So what does the magnitude do? The magnitude stays the same. So when you're doing any of these particularly binary quadrature, there's no amplitude component on it. So it's just going to have some rotational or phase or frequency aspect. So the phase will increase linearly with time from 0 to 2 pi. So it's moving, rotating. Okay. So, you know, I is a cosine phi of t, and which also equals a cosine omega naught t. Okay. So fairly uninteresting. Okay, so noise, right? So different types of noise that might affect you or you might be concerned about with this. Public enemy. So you could have, again, we go back to our ideal signal. There's a cosine 2 pi ft plus phi. So there's an amplitude component. So in this case, it's saying that's a fixed amplitude, right? F is fixed and phi is fixed. So realize that any or all of those components can actually have a noise component to them too, right? So obviously in the real world, you always have AM noise. It's hard to even get rid of it. That's why in your car, like on the AM radio, you hear the whistling and stuff. You plug your phone in, it's not happy because it gets on the power line, things like that. But you see here where the real world signal, there's A, which is the fixed amplitude. That's what we made it to be. Then there's an E of t. So that's random amplitude variation. So that's the real world noise environment, right? 2 pi ft. So there's actually potentially a frequency error. This usually isn't quite as bad. But then there's phi of t. Okay, so random phase variation. So this is really common, particularly when you make the oscillator that is your LO, for example. You can't make a perfect signal like that, right, that has infinitely narrow bandwidth. It never looks like a straight line. It has some width associated with it. So this width, really, how narrow it is, largely is determined by how good an oscillator it is. Okay. So getting into noise on a phasor diagram, so what are the components of the noise? So if I look at that vector, right, so I had that vector, the green line, which basically is my desired signal. The reality is I'm going to have some errors associated with it. So phi of t of the vector is like a rotational error, right? So if you looked at that dot in the constellation, you'll see a constellation in a minute, But instead of being a perfect dot in one spot, it's going to move a little bit like rotationally. And you'll see it. It's actually pretty cool in a minute. So that's a phase error term. Then there's an amplitude error term, is that length of that vector going. So if you take those two in combination, that point, which is the dot or the constellation point, is going to kind of spread out in space because it's rotating a little bit back and forth, and then its amplitude is getting varied also so that that dot gets bigger. Question?
So I can understand amplitude being able to vary because of varying attenuation. How does the phase, is that due to your electronics?
Yeah, so I mean, the most common case is if you get an oscillator, so if I go and buy an oscillator, from whatever, Mini Circuits or somebody, it doesn't look like that, right? A perfect oscillator would have no sidebands, no energy other than at that exact frequency. The reality is it has what we call phase noise. So basically there's energy that's spread out a little bit away from the carrier. So that extra energy is actually the phase variation of the carrier signal. So that gives you that rotate. Yeah?
IQ modulation used for anything
Other than digital?
Is it used for analog type of modulation?
There's cases where one could, but I mean, the most common thing that you would care about would really be for this. Yeah. Okay, thermal noise. Obviously, thermal noise is just there, and you have to deal with it. It's sort of modeled by, resistor, terminals of a resistor. That's the minus 174 dBm per hertz. It's distributed evenly. So, when you look at noise, like we had phase noise where we have a carrier and it's sort of spread out a little bit. That's one type of noise. Amplitude noise is that signal going up and down a little bit. But then thermal noise really has nothing to do with your circuitry. It's just the real-world environment that we're in. So forget about spurs or interferers or things like that, but just the real world has this broadband noise spectrum, which is what we typically call KTB. And it's the standard number people use is minus 174 dBm per hertz at standard temperature. And we'll get into that in a little bit. So it's not dependent on the absolute value of the resistance. It does increase with temperature. And it's usually given in a per hertz. So when I say minus 174 dBm per hertz, it means in a 1 hertz bandwidth. So typically what you'll do when you're modeling a system is you're going to say, well, my system is 1 megahertz. So instead of 1 hertz, you're going to say, well, what's my noise floor? Well, if you have 1 megahertz, that's 1 times 10 to the 6, right? So if I do that in dB, and you can do hertz in dB too, that's 1 times 10 to the 6, which is 60 dB, right? So minus 174 plus 60 is minus 114, right? Just simple math. And so that's telling me in a 1 megahertz bandwidth, that's what my noise floor is. Does that make sense? Did I go too fast? Please speak up if that didn't make sense. Okay. Okay. Yeah, so, sorry, I got ahead of myself. So anyways, that's how I did that calculation. And I think this was mentioned, but, we do hand out these slides later, and, ping me if you need help. Okay, so then we talk about noise factor or noise figure. Okay, so the last conversation was just environmental noise, but then components add noise too, particularly active components. So, when I have an amplifier, so this triangle up top, the amplifier, it's going to add noise to it. So the intent is it's going to just have gain on my signal. So when I put a signal in, so I really love this picture because it really makes the whole thing make sense to me. But if I have a picture and I want to just amplify that picture and make the picture bigger, right? The goal is this picture looks exactly the same as over here as it does over here, but it's bigger, right? Well, the reality is, an amplifier it's not perfect. It doesn't just make this bigger, it also adds a little bit of noise. And the better the amplifier, the less noise that it adds in terms of a low noise amplifier. And the stuff you can get now, it's pretty amazing. When I worked at TRW years ago, one of my colleagues had he said he did his PhD on low noise amplifiers, and he made an amplifier that had like 12 dB of noise figure, and that was like awesome back then. Like now they're 0.5. So it barely adds any noise at all if you get a really good one. Anyway, so how it's defined, you take the signal to noise ratio in, and then the signal to noise ratio out should really just be the in plus the gain, right? Or multiplied by the gain, depending if you're doing dBs or not. But this is also going to add some noise components. So this NN times G is the gain component, but then it's adding a little bit of noise. So that NA is really what the component is from the additive noise from the device. Okay? And it's a function of the physics of the device. So the standard definition of it from the IEEE is noise factor. So noise factor is linear. Normally you're going to talk more in dBs, right? So you'll talk about noise figure, but it's NA plus KTB, G, blah, blah, blah. So, but this isn't the one you'll normally use. So noise figure is 10 log F. So the next thing of interest is very often when you design a system, you don't just have an antenna. Yeah, question.
Where do you get the NA value?
Let's see. That's from the, hold on. Yeah, that's the characteristic of that device. So it'd be in the data sheet, right? But normally, most devices, they don't give you an NA. They'll give you a noise figure. So you could calculate it from the noise figure, but yeah, good question, though. Okay, so, and noise figure is 10 log of F. So the next thing is, when you build a system, typically it's not like a antenna, an amplifier, a filter, and then a receiver. There's some chain of things because you might want to do different things along the way. You might want to change the signal levels. You may want to sample it, change the gain, things like that. So a typical receiver might have a chain of amplifiers daisy-chained along it. So one of the questions is when I look at a chain of amplifiers, so say I had a 10 dB amplifier followed, so G1 is 10, G2 is 10, so the overall gain of those two amplifiers is 10 plus 10, right, in dBs. So that's easy, but what is the noise figure? So the noise figures don't just add. The noise figures, really the kind of interesting thing is they're really a function of the gain in front of the stage preceding that device. So typically, if I was trying to make a low noise receiver and I needed lots of gain, I'd put an amplifier here that had a really low noise figure and fairly high gain. But then when I got to this one, I don't care as much about the noise figure because the gain of this one is really kind of hiding it. So you see here, when I get the overall noise figure, you have the first one is directly that. Plus you're adding the next one minus 1 over the gain of that. So, you might have a thing where there's mixers and all kinds of things, and you want to get the overall noise figure, but to get it, if I'm trying to optimize this thing, then I put the best noise figure here, and I don't worry about it later on. And there's other things you care about later on that I'll talk about later. Questions? Okay. So it's just showing you an example. I take the first stage is a loss, and that often might happen. You might have an antenna and some cabling or whatever to get to the first antenna, so there's some loss, then the stage 2. So incidentally, if you have loss, that is the noise figure, right? So if I have 10 dB loss, the noise figure is 10 dB. If I have 20 dB loss, the noise figure is 20 dB. So it really comes into play in terms of a device, more of an active device. So taking the Cascaded, you see here I just add those gain terms, but then the noise figure I actually have to go through this equation. Okay, same thing down here. So So obviously you can see in this case, putting the amplifier before the pad, I get way better noise figure, right? The cascaded noise figure, while the gains are the same, the first one, I have a noise figure of the cascade is 15. So for those of you down there, it still works, 15 and 15, right? So then the second one, when I just rearrange the order and I put the amplifier first and then the pad, you can see here the gain is 5 instead of 15. So the same overall gain, right? But the cascaded noise figure is dramatically better. So, a lot of when you design a system or a chain, it's really figuring out what goes where and why. Okay. Yeah, I'm sorry? Sure. This one?
Yes.
Okay.
So on the bottom,
Yeah, this one.
it's minus 10.
So minus 10 is, yeah. So it basically I have the same two components, right? This one is a 10 dB attenuator, 10 dB of loss. Same thing here, 10 dB of loss. I have a gain stage of 25 dB. Same gain stage, 25 dB.
Okay, I got it.
Yeah, okay? Good. Okay, so spectrum analyzer noise figure. Spectrum analyzers, guess what? They're receivers, so they have a noise figure associated with them. And, if you compare ones from now versus ones from 20 years ago, I mean, they used to be, even with LNAs and stuff, you might have a 25 dB noise figure of your spectrum analyzer, so that's why you would almost always have to put the preamp in, but now they're much better. So the spectrum analyzers are receivers, and they do have a noise figure. They typically don't specify them. It's probably not a good number usually if you take kind of extreme examples. So that's a lot of why they're not specified. But they give you a Danel spec. So displayed average noise level. Okay, and this is how it's calculated. Be calculated, F is from Danel plus basically 174, and then noise measurement error. So different detectors, there's a different error term, and I'm not going to talk about that, but it's a thing in a spectrum analyzer. And then there's a filter error, so that's how it came to these numbers. It's not normally something you would have to do, so I'm not going to go into it in a lot of detail. And often the spec N is the limiting factor in making these measurements, the noise figure of it itself. So when they talk about a preamp, it's basically an amplifier inside the spectrum analyzer. It doesn't have to be inside. You can externally use one. The nice thing about using one inside the spectrum analyzer is it actually calibrates it and figures out what the noise figure and all that is by itself. Do you have a question? Or yeah? What's that?
The difference between a spectrum analyzer
Oh, good
and a
question.
network analyzer.
Okay. It's a bit of an aside, but that's no problem. Okay, so a network analyzer, first off, it's a stimulus response device, right? So I'm putting in a signal, and I'm looking at what the resulting signal is. And it only generates sine waves. It will only analyze sine waves. Anything else it does, time domain or whatever, is math it's doing, but it's purely a sine wave device. And it's really optimized for doing S parameters. So a spectrum analyzer traditionally used to be, when it first started out, it was looking at frequency content, or power versus frequency, or frequency versus power. How much energy do I have in some specific frequency or band? So that's really fundamentally what it does. But now they do a lot more than just that. They actually do demodulation. They'll characterize different types of standard-based signals. So we can do more generic signal using vector signal analysis, and I'll talk about that a little bit later. But basically, if you say, I want to put in an 802.11a signal, and I want to look at the constellation at the output, and I want you to tell me what's the error vector magnitude or whatever, it can do that, whereas a VNA will only tell you what the sine response is.
So essentially a network analyzer has a transmit and receive,
Yes.
whereas a spectrum analyzer is just receive.
That's correct. but also a network analyzer will only look at a sine wave. No modulation, no nothing. Good question, though. Yeah. Okay, so a lot depends on, first off, the spectrum analyzer and the settings on it. But typically, to get the lowest settings, if you said, I'm going to disconnect the input, I want to get the noise floor as low as I can, right? So the first thing you're going to do, disconnect the input, because you don't want to blow it up, right? And then you're going to go to attenuation, and you're going to set the attenuation to 0. The default is 10 dB, so you don't blow it up. Right? So that's the first thing you can do. Then you can reduce the bandwidth. So there's a resolution bandwidth. So the resolution bandwidth is telling you how big a chunk I look at a time. Right? So obviously if I look at a 1 meg chunk, as I talked about earlier, 10 log of 1 meg is 60 dB, so that sets my noise floor based on that. So I can reduce that by narrowing the IF bandwidth, but then it moves slower. Right, because it goes ka-chunk, ka-chunk, ka-chunk in that size of piece. So that's the next thing you can do. But then there's also you can change the detector type, so that'll measure noise in a different fashion. And then finally, there's a noise calibration routine. So typically, a spectrum analyzer, as I mentioned, has a noise figure associated with it, right? So what that will do it'll terminate the input of the spectrum analyzer and measure the noise figure of the spectrum analyzer under those given conditions. And then it'll remove the noise figure of the spectrum analyzer. So that's as low as you can get. And I think, depending on frequency, I think we can get down to like minus 171 dBm per hertz, something like that. But if you want to do that, I can definitely help you with that. That's a different question. But yeah, right. Another question? No? Comment? Yes. Yeah, FFT is fine. In fact, you're better off in FFT mode. Yeah, it's much faster. I mean, depending on the situation, you might find it's orders of magnitude faster. Yeah.
But don't you have to have a wider bandwidth in order to then have the FFT work? So now you're...
Yeah, but all that... But no, it's not, because if you have a wider bandwidth, you have a faster time constant, right, in terms of the analog bandwidth. But then when I do the narrow band filtering, the binning in the FFT, it's done all digitally. So it's much faster. It can do those processes simultaneously in parallel, so it's much, much faster. Okay. So for further reading, Y factors. So this is about noise figure. There's other means of testing noise figure, which I won't go into, but if anybody's really doing noise figure or interested, let me know. Okay, so phase noise. This is another one that I talk about a lot. So, phase noise, if you're an RF person, you look at the spectrum of it, right? And again, if you could make a perfect straight line up with no bandwidth associated with it, you'd make $1 zillion and you could retire. So the closer you get to that, typically the more and more expensive it gets. So that's RF guys. RF guys care about this spur. But then time domain guys, so if I'm talking to Xilinx or Cisco or something like that, they really care more about, I'm looking at a square wave, and that thing's, instead of looking at the energy, I'm looking at that thing's phase moving around, right? So it's jitter. So it's a time domain event. But in actuality, that jitter is the same thing as phase noise. Okay, so if we're looking at a periodic signal, and I can only do this with a periodic signal, but if I look at the phase noise of a periodic signal in the frequency domain, I'm going to see a spike. Okay? If I look at it in the time domain, I see a sine wave. And how much that sine wave moves back and forth is the jitter, and how much energy is is moved outside of that spike is the phase noise, and one can be determined from the other. And typically, a lot of people measure jitter on a scope, an oscilloscope, and on an oscilloscope, what's nice about measuring jitter is it doesn't have to be a periodic signal. So if I'm looking at data jitter, data-dependent jitter, that signal isn't necessarily 10101010. It could have 11001, some random pattern, and you'll get a statistical distribution of this variation, right? So that's called data-dependent jitter. But if it's a periodic signal, I can look at it as phase noise, and it's really the same thing. And I can measure phase noise much more accurately with much more dynamic range with a spectrum analyzer, or actually a phase noise analyzer, than you can with a scope, because I can vary the bandwidth that I'm looking at. So if you remember when I'm talking about the noise bandwidth, changing the noise bandwidth as a function of resolution bandwidth filters, things like that, I can't do that on a scope. A scope pretty much looks at a broadband thing, and it's going to take that distribution. So I can't change the noise levels that the analyzer sees. Plus, I typically, on a spec an or a signal analyzer, I have more bits of resolution in my measurement. Okay, so some typical devices. There's a VCO, or crystal oscillator. Obviously, a crystal oscillator is intended to be something fairly stable, and there's different... Comment? Question? Okay. So the crystal oscillator is tended to be a fairly stable oscillator, and there's varying degrees of how stable one can make it. There's ones that have things to control temperature effects, to help dampen vibration effects, things like that. So that's kind of a more stable reference oscillator. And then if you look in a phase lock loop system, this is kind of the reference fixed frequency. And then I use this voltage control oscillator. And guess what? What a voltage control oscillator does is it gives you a frequency as a function of the voltage input, right? So I change the voltage on that VCO, and I get a different frequency. So I'm going to really usually use both of these together in a phase lock loop system to get some very stable output frequency. And there's other things one can use, a YIG oscillator or a DRO. These are kind of more fancier things that I'm not going to really talk about in great detail. I'm sorry? Yeah. Oh, which of those? We use all of them in different areas, kind of depending on frequency, whatnot. But yeah, we use all of them.
So in the high end, do you use YIG also?
We use pretty much all. I think most of our instruments have YIGs in them, particularly if they're going higher in frequency. Yeah. Yeah, you're welcome. Okay.
Phase noise to jitter.
I'll talk about that. So, I mean, it's basically, we have a tool to do it, but it's basically, you're going to do some integration over some range, but I'll get back to you on that one. But they do go back and forth. It's a good question. It's a very good question. Okay, so, I'm not going to go into a lot of the IEEE definition and all that, but basically if you look at phase noise, the unit of measure is L of F. That's from Leeson. He was one of the original guys who studied this effect. But they actually changed the definition of it some time ago, the IEEE definition, and it's 1/2 the spectral density of phase fluctuations. So what that means is if you look at this diagram, really, this phase fluctuation really is this whole curve. So going from, everything to the left and right of the straight up line is the phase fluctuations, right? Or frequency fluctuation, I'm sorry. So this is frequency on the horizontal axis. So, so that phase fluctuation will give you a corresponding frequency fluctuation. And that definition is basically saying if you take this whole curve and you chop it in half and normalize it to 1 hertz bandwidth, that's the definition of phase noise. Yeah?
So if you take, let's say, a 10 megahertz oscillator,
Yeah.
and you look at it with the spectrum analyzer,
Uh-huh.
and you have a bandwidth set to say 10 hertz or something like
Yeah.
that, is the phase noise of a typical crystal oscillator more than 10 hertz away from the frequency?
Well, so it's not really so much that it would be 10 hertz away. It's that it's, you know, if you had a 10 megahertz oscillator, let me go to the middle. I feel bad when I go to one side or the other. Anyways, so if I had a 10 megahertz tone here, right, the point is it's designed to be 10 megahertz, right? So the main energy is going to be at 10 megahertz. And if you look at it, that's going to go much higher than these curves. But they are there. So, you know, what you're really measuring is how imperfect is it from 10 megahertz? How much energy does it create other than 10 megahertz?
But you're trying to measure the energy that's not at 10 megahertz, right?
Yeah, basically.
If the spectrum analyzer's bandwidth filter is 10 hertz wide, what I'm wondering is,
Yeah.
narrow enough to be able to actually see?
Yeah, I mean, normally that's kind of, it depends on how good the oscillator is. But you'll typically find, like, if you look at a typical oscillator and you get really in close, it might be only 50 dBc down. So you easily can measure that. Question? Sorry.
Could you think of it in terms of like your clock is going to be 10 ppm, and for 1
It's-
megahertz,
yeah.
10 ppm, doesn't that translate to?
It is the
10
same thing. You're absolutely right. Yeah.
So a 10
Yeah.
ppm would be 10 hertz wide on that.
Right. Yeah, in terms of ppm. But the bottom line, thank you, that's a good point. But really the bottom line is that, you know, particularly when I'm looking in close, this thing is pretty high, right? So relative to the noise for the spectrum analyzer, I can see it no problem, unless it's an amazing oscillator, right? So as you go out further, it gets harder and harder to see because at some point you're going to run into the noise floor of the analyzer itself. And there's some other issues to worry about where you need a phase noise analyzer instead of a spectrum analyzer. But all said and done, you know, it's can I resolve that signal within that bandwidth? And at that level, it's not a problem at all.
We can get like a phase noise option. Any normal spectrum analyzer
Yeah.
should be able to measure phase
So, and I don't think I have in this presentation. It's a conversation we could have another day. But so basically, the key thing is when you measure a spec. In fact, I do have some slides on this. But you know and I'll talk about this in more detail in a bit. But the key thing is when I use a spectrum analyzer, right? Forget about all the FFT stuff and all that. But think about it as like I have a signal. I'm going to mix it down, and then I'm going to give you an amplitude level, right? So that tone that I use to mix it down with, it has phase noise on it too, right? So there's limitations in the spectrum analyzer itself in how well I can resolve that noise if I want to get better than that, right? So it really depends on the level of your device that you're trying to measure. And I have curves and stuff on that, which I'll mention later. But if you have a really, really low phase noise thing, you definitely need a phase noise analyzer. And we like to sell those. They're really expensive. But anyways, I'll get into that a little more.
Why are we looking at the frequency variation of this phase noise when you're actually restricted to digital signals?
Well, I'll get into that in a minute. It's a good question, but it's basically I'm getting noise on my signal, right? It's unwanted signals, so it's making my signal look wrong for all intents and purposes. Okay. Okay, so if you look at phase noise, so this is actually a fairly typical plot of a PLL type oscillator. So you'll see here there's some slope here. This is really kind of inside the loop bandwidth of the PLL, so it has to do with the loop filter. Then there's some divider noise, etc., VCO noise. So the characteristic shape of this is common of what you would see for a PLL type oscillator. And, you know, there's different, depending on what the person is doing with this oscillator, they care about looking at it in different ways, right? Some guys may care just at specific offset frequencies. So they'll talk about spot noise. But then other guys may care about the overall energy. And I'll get into that a little bit later. But it's really the same thing. I can basically integrate the area under this curve to get what's the overall phase noise over that range. Okay, so that's integrated phase noise, residual FM. So these are all really the same thing. So here's somebody asked me, how do I get jitter from phase noise? That's how you do it. That's the hard way, right? Or if you have the right analyzer, it just tells you. That's the kind I like, but you basically get it integrating. And if you have something where you're measuring it already, I actually have a spreadsheet where it kind of does that integration where you can put in a range. But it's basically you're integrating the phase noise and then doubling it and then dividing by 2 pi c.
But jitter is time domain measurement.
Yes, correct. Correct. Okay. Yeah, but remember, jitter is in seconds, and phase noise is in L of f, which is really 1 over second. So, okay. So measurement limits. So basically, you know, I talked about that little cloud of the error vector there, right? So KTB is minus 174 dBm per hertz at room temperature. But that actually has an AM and a phase component. So there's an amplitude and a noise component. So the theoretical noise floor of these is really minus 177 because it's basically, can I go all the way down here, all the way over here, or all the way over there? So the phase noise is expressed, as I said, dBc per hertz. And it becomes minus 177 minus the signal level. And here's an example. But you'll never get anywhere near that, so I wouldn't even worry about it. Okay. So if you were to do this with a spectrum analyzer and a phase noise analyzer, in terms of making the measurement, it's really more or less the same, unless you want to do something fancy. You basically connect the DUT to the spectrum analyzer, and if you looked at like a normal spectrum measurement, you would see just, you know, the spike. If you put it in phase noise mode, it's going to show you that curve, right? And it'll tell you, you know, depending on how you set it up. Do I want, you know, the phase noise at given offsets? Do I want the integrated phase noise? Do I want the jitter or whatever? And it'll tell you all that. Okay, but it's simply put that in, connect it, and then put it in phase noise measure mode. And what do you see? So, go over here for a minute. So, this is manual spot noise measurement. So it's basically, this is in a spectrum analyzer mode, right? It's not in phase noise mode. So you see there, I can set the marker. When you go to the marker function, if you've played with a spectrum analyzer before, you'll see that the spectrum analyzer will let you look at different things with that marker. Maybe I care about a relative amplitude to another, or relative frequency to another. Maybe I care about marker in terms of noise, or things, different things. But you can put it in a noise mode, which normalizes it to a 1 hertz bandwidth. So marker noise mode, this is kind of the simplest way one could look at noise, right? It's normalized to a 1 hertz bandwidth. But you don't know anything about that noise, phase noise or amplitude noise or whatever. Okay, so somebody just asked me about a spectrum analyzer. So this is very roughly the architecture of an FSW. So there's multiple down conversions depending on frequency or where you're going or what you're doing with the signal. But you can see here there's more than one LO, right? So when you mix an incoming signal with that signal, the output is an RMS in terms of phase noise of that input signal, the output of the first mixer, if I have an RF in, it's going to be the RMS of the two signal inputs, right? So that's adding noise right there from that LO. Then I go to the second LO, and I have the noise from those two, and then I'm going to add more noise from LO2, and then I'm going to add yet even more noise from LO3. So in general, a spec N is not optimized for measuring phase noise. And, and to boot with that, these LOs, when you have a spectrum analyzer, if you want an LO to move a lot, it means it's going to be more sensitive to voltage variations, right? Because it's got to tune over a wider range, which means it's more sensitive to noise. So that's kind of the limitation in terms of the spectrum analyzer. But how do I care in the end? This is really telling you the internal phase noise of an FSW spectrum analyzer. All our spectrum analyzers have a similar curve, but it tells you at some given frequency. So if I take 1 gigahertz, the orange curve, that's this one, it's basically saying that the phase noise floor of that analyzer follows this curve. So if I'm measuring above this curve, my device, in terms of phase noise, then I'm probably okay using an FSW. If I want to measure below it, forget it, all bets are off. And to add with that, if you want to know what sort of margin I want, right? So say I want to have a measurement error of 0.04 dB. So down there, that means I need to have 20 dB between my signal and this signal. So that would mean to get that 0.04, your curve of your DUT would have to be 20 dB higher than that, if that makes sense. And if it's not, and you want that, then you need a phase noise analyzer. So that answers your question, I think, hopefully. And we make those too, so we got you covered. So if you go into the phase noise measurement personality, so before I showed you just normalized noise, so this is basically telling the spec N to measure phase noise. So it's following that curve I just showed you. The spot noise, this is kind of the default. It'll tell you at these given offsets, this is what the phase noise is, right? Then it'll tell you if there's any spurs on there, right? And what are the spur levels, okay? Then it'll tell you what's the jitter, integrated jitter. It'll tell you what the FM is, the phase modulation, and the integrated phase noise. The other thing that's cool, like if you're more of a digital person and you care about jitter, it'll actually tell you in the spur list, each one of these spurs has jitter associated with it, right? So it tells you the power level and the jitter of that particular spur. So you get lots of information. Okay? Question?
Is phase noise a single number that identifies the quality of an oscillator?
It's,
Hertz looks like
yeah.
it's a measure of the energy at a given distance from the carrier. Doesn't look like it's a single.
No, it's definitely not a single number. It could be a single number if you integrate it over a range. Like some people say, I want to know what's the integrated phase noise from 1 hertz to 1 megahertz. So you'd take that energy and you'd integrate it and you'd get one number.
And then away from the carrier.
Just over that region, right? But some guys care about at a particular offset, right? So that in that case, you would say, what's the phase noise, not the integrated phase noise, the phase noise at 1 kilohertz offset from the carrier? Or what's the phase noise at 10 kilohertz offset from the carrier, or 100 hertz or whatever? So typically those guys would get multiple numbers. But then some guys want the integrated, so they just want one number that says, tell me everything all added up together over that entire range.
I think someone might have already asked this, but
Yeah.
if you have a 10 megahertz sinusoidal oscillator,
Uh-huh.
let's say,
Yeah.
and you're looking on a spectrum analyzer,
Mhm.
say a kilohertz away from the carrier.
Yep.
How do you know how much of that energy a kilohertz away from the carrier is from phase noise and how much of it is from amplitude?
Amplitude. That's a great question. So that curve I showed you that had the different graphs, if you are above that curve, it knows that it's phase noise. Actually, the way it measures the way it does the measurements, it does it with INQ as opposed to just an amplitude detector. So it has a lot of ability to determine between phase and amplitude variations. But that's the limiting factor. If you want to go below that, you will run into that limitation. But then you would go to a phase noise analyzer, which is specifically designed to measure phase noise. Okay? Okay. Take a breath. Let me get some more water. Okay, so yes.
So sometimes when I'm trying to measure the phase noise,
Uh-huh.
especially on the digital signal, and sometimes it seems like it's hard to track the carrier information.
Yep.
Can you make some suggestions? Let's say, especially digital signals, I guess it's kind of hard to
Yeah.
track. Are there any tips?
So what is your DUT? Is it a VCO or something else?
Yeah, let's assume it's a wireless signal.
Okay, so I guess the first thing is, if you were measuring a VCO, which is probably the worst case scenario of that problem, that means that whatever voltage that tune voltage is seeing determines what the frequency is, right? And if you had a crummy control voltage, that thing's going to move over a hell and gone, obviously. So in that case, we actually have a tool for measuring VCO. So we have a voltage source on the phase noise analyzer itself, which will be able to track that. So that's one case. But to some extent, it really depends a lot on how much it's moving. I mean, you can put like a frequency tracking on. So like if you're in a phase noise mode, within a reasonable range, it should be tracking the frequency of the DUT. Like in a phase noise analyzer, it's designed to work. It actually has two different bands for measuring that. So it can work. It can deal with a lot more error associated with that. But basically, if you have frequency tracking on, it should do it. And if you have a problem, you're more than welcome to call me, and I can help you with it. You're welcome. Okay. Any other question? Let's see what I got in here. I don't think I want to give my glasses away. I got a few things in here, so I'm going to just get rid of them all. Looks like they're all more or less the same thing. We have more or less one more section to go, one and a bit. Okay, so I got lots of these. Looks like a battery thing for USB. Anyways, and anybody need an HDMI cable? If you need one, you can have it. You were the only one who raised your hand. Okay, so I'm going to give those away as we go. Okay, so digital modulation, constellation diagrams. So now we're going to kind of get into what does it look like after I've done the stuff we just talked about. So I made that quadrature I summed together, as we talked about, that INQ stream, and what does it look like on the constellation. So that dot now actually represents 2 bits of information, right? If I'm doing QPSK, oh, I'm sorry, this is BPSK, so it actually represents 1 bit of information. So I'm not really using the quadrature right now. But basically, because I'm doing BPSK instead of QPSK, this side is doing nothing. So it's really, I'm just doing that. The quadrature's not even part of the equation. So basically it's saying, when I send information in that constellation diagram, it's going to go back and forth depending on whether it's a 1 or a 0 on that diagram. So then I go to QPSK. Okay, so now I'm going to have information on both lines. Okay, so I put in a 1 in both of them, and I'm going to go up here. And realize that while on this diagram I'm showing the point here for 1, 1, it isn't necessarily 1 here. This is basically, you define what this map is. You get to say 1, 1 means I'm here, or 1, 1 means I'm here, or here, whatever. You define that in your map diagram. So if that's 1, 1, then that would be 0, 0 down there. That's, what is that? 1, 0, 1. So anyway, so that's how it works, basically. But the bit rate is half the symbol rate. So it basically means the thing I'm transmitting here is going slower than what's coming in. Okay. So if I look at the different constellations, BPSK, there's 2 points, right? Binary, like that. QPSK, quadrature. So that means there's 4, right? Quad is 4. There's a thing, 8PSK, and there's a few things that were around that did that. You don't really see this all that often. Really see variants of this, including an amplitude level, and you'll see that in just a minute. The rate at which symbols are sent is the symbol rate, and other than BPSK, the symbol rate does not equal the bit rate. Okay, so the data rate is the symbol rate times the bits per symbol. Right, so QPSK, I'm sending 2 bits per symbol. So a symbol rate of 1 megahertz is a bit rate of 2 megabits per second. Again, if you look at that in the frequency domain, so now I'm going to go look at what the spectrum looks like. Really, the symbol rate is going to determine the bandwidth, not the bit rate. So if you can cram more information in the same amount of spectrum, obviously it's more spectrally efficient. So, you know, the FCC and those kinds of guys, or the Sprint or whoever who buy this spectrum, obviously they want to cram as much stuff in there as they can. So they like being able to put more bits of information on a symbol. So there's other higher levels. So we started out at QPSK. So the middle 4 dots on the left, the middle 4 dots is QPSK. So that's basically quadrature phase shift. So I have 1 level of amplitude and 4 phase states. 16 QAM, now I have 4 bits. So instead of 1 amplitude level, really I guess 2 because binary is 0, 1, but I now have 4 different amplitude levels. So I still have just the quadrature. So there's really 2 phase states, all said and done, in my modulator. But because I have the different amplitude levels, that's going to give me 16 combinations, right? So going from here to here has the same amplitude, the same phase vector as up here, but a different amplitude vector, right? And so this has a different phase from this, et cetera, et cetera. So taking that phase and amplitude, I can get more dots, which represent, instead of 1 bit for binary, 2 bits for QPSK. Now I'm at 16 QAM, so that's 4 bits per symbol. So now if I want to send, if I want to have yet more spectral efficiency, I can use 16 QAM. But obviously, this has now an amplitude component. And if you remember from earlier, the noise issues are more challenging with amplitude. So the more amplitude levels I have, the more potential noise sources I have. Question?
Before talking about encoding,
yeah.
What's the relationship between data rate and carrier? So how much faster does your carrier need to be than the data rate without doing any encoding?
I mean, the carriers really has nothing to do per se with that. I mean, the carrier is basically the signal that I'm going to transmit the information through free space with. So, I mean, obviously it's higher, but typically it's orders of magnitude higher. I mean, like.
So is there anything fundamentally limiting me from putting a gigahertz data rate on a 10 gigahertz signal? Does it affect SNR or anything like that? It's just...
Yeah, I don't think so. Yeah, I think it's a bandwidth. Yeah, I mean, when you build components and stuff, one typical challenging factor you have is when you do things, say I want to increase the bandwidth of an amplifier, for example. It's typically a function of a percentage of the bandwidth of the carrier, right? So if I want, 10 dB of, or 10% bandwidth on a 10 gigahertz amplifier is, this difficult. But if I made that a 1 gigahertz amplifier, to get the 10%, it's obviously a smaller number. So usually you'd use a higher carrier frequency if you want a wider bandwidth, because it's, as a percentage bandwidth, it's usually much easier. So, okay.
The previous slide,
Yeah.
you showed a bandwidth of 1 megahertz. You have a fixed frequency for digital modulation. So
Yeah.
how do you get a bandwidth over there, 1 megahertz?
This is from the symbol rate.
You should have a
It's from the symbol rate, right? So the symbol rate of this is 1 megabit per symbol. I'm sorry, 1 megasymbol per second. So the symbol rate determines the bandwidth.
what's the diagram showing?
It's showing, this is if I'm looking at a BPSK signal, so it's modulated on the carrier, ready to go. I'm looking at what is the bandwidth of that signal. Okay, now I'm looking at a similar carrier. It's actually the same carrier, but instead of having BPSK, it has 8PSK. So it's a different type of modulation that has more bits per symbol, right? This has 1 bit per symbol as opposed to 3, but yet they still use the same amount of bandwidth. That's really the key takeaway there.
What it means that it turns out to be an AM type of modulation.
In this case, it's not, but there is a case. So when I'm talking about 8PSK, remember 8PSK is just rotation, right? So I have 8 phase states, but no amplitude. But in actuality, the thing most people do is this. There's an amplitude component and there's a phase component. So this is the most common thing that you would see. Okay? Any other questions? Is that clear? Okay. So if I look at that IQ modulator example, so obviously when you make this stuff, there's a lot of other stuff back here that is behind the curtain for me. I'm an RF guy. But you would have to take, you'd have to take your bit stream and then you'd have to divide it into, or make it into a multi-amplitude signal from probably an A to D, and generate this and then split the bit stream, which would then feed the IQ modulator. And then this gets sent out somewhere. Okay. Yeah. Okay. So you see here as I'm transmitting different bits of information, they have different amplitude and phase components. You can see here I'm generating that 16 different dots on the screen. Okay? Okay, so
It's like very bad picture over there. It's overlapping.
it's just it's not a real thing. It's just a simulated thing. Yeah, it would suck if that was. I'll give you that. Probably wouldn't work. And actually, that's a good question. So, what problem do you have if that was real? If that dot was so big that it was going over the. And why?
Because they are overlapping.
Right. So it doesn't know, is it that or that, right? Yeah, exactly. So, yeah, that wouldn't work. You're right.
Apply error correction.
Possibly. Yeah, depending on, the characteristics. So, obviously nobody ever makes this like this. Your constellations don't have to be those particular dots on the screen. This is, I work for a German company and they like beer. So that wasn't my idea. That was the German guy. So, and that's Orion, I think. Orion constellation or whatever. So, another type of modulation is FSK. So, for prize, anybody know what the most common thing that you probably all have in your pocket that has FSK on it? Key fob. All right. Here. Here, have a, sorry, bad toss. There you go. Have a prize. Okay, so yeah, so FSK is basically, I'm changing the frequency in some more like binary fashion as opposed to an analog variation. And then there's a special case of FSK where we use MSK, and that's really kind of a spectral efficiency thing, but I'm not going to get into that in any detail. What does that look like? Here's the IQ diagram. This isn't one I use very often, so anyways, I'll skip that. Okay, so other considerations. So we did that. I don't know what it's asking. Oh, yeah. Okay, so what does the spectrum look like? So we talked about the bandwidth and whatnot, but what does it really look like in the real world? So fast transitions. So when I go from this crappy-looking constellation point to another one, which doesn't really look like that, but depending on where I'm going and where I'm coming from and where I'm going to, you get different frequency and amplitude components in the trajectories. So if you look at, there's a constellation diagram which is just the dots, but then there's another diagram where you're looking at the actual constellation showing the transitions. And the thing that you find is often if you take a transition where you go from the lowest voltage, so maybe down here, to the highest voltage, obviously that is going to require the most current, the most potential nonlinearities, and the more settling time. So a lot of these are really designed about trying to minimize that. But a thing that we look at in terms of not even doing that yet is what is if that's the spectrum of the signal, obviously this is a very wide signal. Okay, so that previous spectrum I showed you had filters on it. Okay, so if this is what the signal looks like, that's a lot of spectrum. That's probably not necessarily ideal. So what can we do? Again, we're seeing these different amplitude transitions. So we put in a filter, right? So there's different types of filters one uses. A rectangular filter doesn't really necessarily get rid of a lot of these other components very well. The best case for that is the raised cosine filter. Then we have a Gaussian, and we'll talk about kind of different reasons why you would use one versus the other. Yeah, or raised cosine. There's both. Okay, so intersymbol interference. So it looks like the cosine is best, right? That's the narrowest, so narrow is good. It means I'm more spectrally efficient. Intersymbol interference occurs when the previous symbol has not completely settled. So again, when I'm going from the trajectory of one symbol to another, and I want to get to that amplitude and phase level before I can stop, measure it, sample it, and then go on to the next one. Okay? So I'm going to trip over that. So intersymbol interference occurs when the previous symbol hasn't completely settled. Okay? So you see here, like in that case, these are smoothed. Okay? So when I'm filtering it, I'm really smoothing out these edges. Right? So if this guy isn't done and been able to settle to whatever the next thing is, it's going to smear into the next symbol. Okay? So what happens is you can get an offset. You see that that constellation point move down, right? So, that's the kinds of things that can happen when I have intersymbol interference. So the ISI-ness of a filter, if I'm using the raised cosine, that's the best case ISI-free. And if I use a Gaussian, there's still some intersymbol interference in there. So, why do I pick one versus the other? There's, as usual, there's trade-offs of things, right? So who has the best spectral efficiency? Who is the narrowest? It's the raised cosine. And which is ISI free, it's also the raised cosine. So why would I ever use the other ones, right? The Gaussian, the rectangular, obviously are not as good. So what's the downside? There's always a downside. So there's looking at the trajectories, which I was just talking about. So if you look here, raised cosine, it has the highest peaks, right? So when you're an amplifier designer, and I know you were an amplifier designer, or amplifier person, maybe, I don't know. Anyway, so if you're an amplifier designer or an amplifier manufacturer, one of the challenges of amplifiers is peak to average ratio. So you hear that a lot in more linear modulation schemes, but it's basically I have to drive that thing with more current. So that thing is less efficient if I'm running it to be able to take a higher peak to average signal. So the raised cosine filter scheme has the highest signal peaks. So that's something that the PA amplifier or power amplifier guys aren't so happy with. So they don't like it. So, in all these things, there's trade-offs. If you look at the entire system, there's trade-offs you have to make. So it has 2.6 dB higher peaks than Gaussian and close to 2 times that of the peak power. So you need a bigger amplifier, as I said. If you have a bigger amplifier, typically one of the more energy-hungry devices in a cell phone or a mobile device is the PA, right? So that's what's limiting your battery life to a large extent, and the heat issues and all that. I'm sorry?
What would happen if you...
You're going to distort your signal.
But from a pinpoint standpoint...
If you clipped, you mean...
So if you still
Yeah.
use the raised cosine, but you don't have the power to...
So then you're going to get to that, you're going to start getting intersymbol interference because you're not actually showing the whole trajectory of the signal. Okay. So what often they'll do is they'll actually use a combination of them. At the transmitter, they'll use a root cosine filter to limit the bandwidth. Root raised cosine, right? And I think we said that was the best one. And guess what? If you think about from an architectural point of view, which side do you care less about being expensive and fancy and all that? Base station, right? Yeah, the base station. The handset, you want to make it cheap and simple. So at the receiver, you could also use a root raised cosine to filter the noise added by the channel. And if you cascade two of them together, you get a raised cosine. So that's kind of one of the more common ones that you would see, but with not as tight a specs. Okay. So alpha is the sharpness of a filter. Not really that interesting. Okay. So mapping, and I mentioned this before, mapping is the label of the constellation points with data values. So, don't think that they necessarily have to be one particular order. I showed you that funky constellation, but, this is gray code mapping. That's a specifically defined set, but it doesn't have to be that. A lot of these things are defined by a lot of history of measuring devices and, what is the most likely trajectory from one to the other that'll minimize current and things like that. So, all of these kinds of things, people put a lot of thought into why would I make it one way versus the other, but you're way smarter than me. Okay. So a differential constellation, so you see sometimes DQPSK. So this is really, instead of looking at an absolute phase and amplitude, it's really looking at transitions. So it's another constellation scheme. So this is pi over 4 DQPSK. So that you can see it's basically like two constellations, QPSK, that are rotated. It looks very similar to a 8 PSK. Okay, so what am I doing on time? Oh, I'm a little ahead of schedule, I guess. See, I told you. So vector signal analysis. So in the end, I'm going to want to analyze all this stuff, right? So when I look at constellations, I want to be able to characterize how well these components work. And in the end, if I look at a system, I care about the bit error rate, right? So I'm going to send bits in, which come from voice or whatever, but I'm going to send bits in, I'm going to get bits out at the other end. So in the end, that's generally what I care about. But if you look at a system and you break it into like pieces, you can't always get bits out of everything, right? So if my device is taken data in and now transformed it to something other than just a bit stream, I want to be able to compare with some metric the quality of the signal as it's gone through that component or group of components. So that's where we use the vector signal analysis. So in our case, what we'll do is we'll take, we're going to have a known signal with idealized characteristics, and then we're going to be able to measure it at different points and quantify what the error term is, and you'll see that in a little bit. Okay, so spectrum analyzer, if you want to measure other than just spectrum, looking at power versus frequency, then you need a VSA. So it's a software component that goes on a spectrum analyzer. Okay. Is it a separate instrument? No, it's not. So what it does, again, there's an IQ DMOD in there. So it's going to take that incoming RF signal, split it into I and Q, and use some fancy algorithms to actually do analysis on different types of waveforms. So in the simplest case, when we talk about VSA, vector signal analyzer, it's letting you define a generic waveform. You can say I have a QPSK signal, and it has this type of mapping, et cetera, and I'll show you that in a sec. And then it'll let you decode it. And you can generate a similar thing on your SIGGEN or device or whatever, and it'll allow you to measure metrics from that device. But we also obviously have lots of software personalities that enable you to use standard waveforms, right? So most people don't want to say, hey, I'm going to invent my own modulation. They want to say, hey, I'm making an 802.11a or N or B or G or LTE or Bluetooth or pick your poison. So we kind of do most of those. So what are the key parameters one would measure in VSA? So bandwidth, we talked about that a little bit, maximum symbol rate, and residual EVM, error vector magnitude. These are the typical VSA measurements you make. And obviously the more expensive one, guess what? It can measure these things better. It has tighter tolerances, filters, and whatnot, digitizers and everything. So QPSK, how would I do this? What are kind of my inputs to my analyzer? So QPSK, what type of modulation? You're going to tell it it's phase shift keying. Okay. And what's the order of the modulation? So it's QPSK. Okay, that could be QAM. It could be BPSK. Mapping, gray. You could have your own defined one. Symbol rate, 1 megahertz in this case. And what's the transmit filter? And more often than not, it's going to be a root raised cosine. And then what's the alpha, filter roll-off factor, is 0.2. Okay, so if you go to your analyzer, you're going to go into VSA and tell it, these are my characteristics. And inside the VSA, the spectrum analyzer, let's see. So you have signals coming in, goes through a transmit filter, okay, the channel. So this is really whatever my DUT's doing, right? Noise is added there too. So then I come in, and I have multiple paths I'm looking at. So if I look at the different paths, there's the top path, the measure, filter, and equalizer. So this is doing channel estimation. So really kind of that's the first thing you need to do to set those for everything else. So it's going to take that channel estimation, and it's going to continually try to keep improving that, right? It's going to make an equalizer and modify that that training sequence so the equalizer closely matches your channel. Okay, so that again gets programmed into here, and then you look at what's going on inside. There's a symbol decision, the transmit filter, and the measure filter. So this is roughly what goes on inside. I don't want to teach you how to make a VSA, but so it's going to calculate the timing sync, frequency sync, and phase sync. It's going to scale the amplitude, make a symbol decision, so it's figuring what points there are, get an error signal, and then calculate the modulation quality. Okay. So again, we talked about this. You had a great comment on that. When those dots get too big, you know, if there's too much error, it's going to make a wrong symbol decision. So what they'll do is when you start a sequence, it's actually going to use a known values, right? So that's why you'll see with a lot of these standards and things, it'll start out with like what they call it a training sequence. So they'll say, you know, for this certain period, first so many symbols or whatever, we're going to send this sequence. So it's looking for that. It's expecting that. And then it's using that to say, okay, I know this is what this incoming symbols are, and I'm going to mess with my equalizer and channel estimator to determine what my coefficients are to optimize what that input signal is. So, measuring error vector magnitude, we've been talking ad nauseum about vectors, right? So when we look at that constellation, you know, it's going to calculate what is the ideal location for that constellation point based on the characteristics of the signal. So then it's going to measure where your symbol location is. So the EVM, or error vector magnitude, is the amplitude of that signal from the ideal location to the actual location. So this is more or less what you're really measuring. Okay, so it comes from 20 log of the error over the reference. Okay, now we're going to get even crazier diagram. So there's the reference vector. Okay, that's the ideal vector. We have the measured vector. Okay, so that's the actual constellation point that I measured. Then I'm going to determine that error vector from that. Okay, and that error vector, there's an amplitude component and a phase component. So I can break those out. There's the phase error vector. So obviously this is parallel to that, but at the origin, so I can measure with reference to the origin. Okay? And that's how much in phase. So you might have I error and Q error. So you can see here, this guy's over here instead of over here. So the I error is this. The Q error is that. The phase error is that. This is parallel to this. So that rotational error is down here. So I'm going to repeat that down the other end. Kind of went off in the weeds. Okay, actually I'll go in the middle. Can you guys see this down there? Okay. So the key thing here is there's the reference vector. Okay, that's the ideal trajectory of the symbols that I'm receiving. And we have the measured vector. So that's what I'm actually measuring with the VSA. So if you look at it, I said we have this error vector that we talked about earlier. And that error vector can be broken down into, there's a magnitude component, there's a phase component, but you can also break that down into an I component and a Q component, right? So if I take this error vector, the amplitude error is taking this guy is the ideal location, rotated, and that error in amplitude is that difference, okay? And then if I take this signal, parallel it down at the origin, the phase error is that with respect to the origin, okay? And then the I error is taking this horizontally. The Q error is looking at that vertically. Okay, so those are pretty much all the different things you're going to look at in the VSA. Okay, so common errors that one measures. Error vector magnitude. So there's error power or mean constellation power. Basically, differences in where the points should be versus where they actually are, but more in terms of amplitude. And MER, so this is really more or less the same thing, but the guys who do cable TV, so like DOCSIS, if you've ever heard of DOCSIS, MER is, the DOCSIS folks have a similar measurements, but slightly different nomenclature. And then Rho, we have correlation ideal signal and measurement of many symbols. So that's more of a correlation thing over a lot of symbols. So both of these things are fairly relative to like cable TV guys. Like, so we make analyzers for doing this type of measurement for cable TV signals. So DOCSIS, you probably have heard of. And so what they'll do is they'll actually collect data over a month. And they'll look at what these signals look like over the course of a month and look at the statistics and histograms and whatnot. Okay. So VSA, the EVM, and other modulation quality parameters. Here's kind of everything that you get out of the VSA. So you can see here there's EVM, MER, phase error, magnitude error. I think I talked about all of these. Power, amplitude, droop. Yeah. So looking at some typical sources of error one might encounter in design or testing. So here's a transmitter. Okay? So here's all the different measurements I'm looking at. So you see here, these are a whole bunch of different errors that you'll see. There's jitter from the clock, compression from the amplifier here, compression, that's in the like I amplifier, Q amplifier, because typically those have amplifiers in them. So IQ offset, that's difference in amplitude or phase between those two relative to what it should be. Carrier feed through is that RF getting through there. Quadrature error is error relative to the 90 degrees. So in this case, I'm using the VSA local oscillator as a reference so I can measure what that error is. Symbol clock is used as a reference of the VSA, so I can actually compare that relative to my device so I can get the symbol clock error. IQ offset carrier feed through. It's going to look at that constellation, and you're going to see here that it's offset. You see it's not centered perfectly. So that's going to be relative to an ideal constellation, which again I have in the VSA. Gain imbalance. What's that going to look like? Looks very similar. And you'll see here these are offset in amplitude relative to where they should be. What's this one? Quadrature error. So these guys aren't where they're supposed to be in terms of phase. They're rotated off a little bit. Okay. So one thing that you can do with the VSA is you can tell it to compensate for these things internally. So you can say, and obviously if you're designing a thing to do all that, you can't just check all those boxes and say you're done, right? That'd be too easy. But it lets you know what things you're compensating for, right? So if you have a huge error in, say, IQ offset, right, and you tell it to do IQ imbalance compensation, and that goes away, then you know that that's something that I need to be looking at in terms of my receiver design.
But do I need to provide the actual expected value of that?
No, it calculates that itself. Yeah.
Calculates, I guess, the ideal case. The ideal
Yes,
case.
correct. Yeah. Yeah. Okay. So, I can compensate for IQ offset, amplitude droop. It defaults to doing channel estimation, IQ imbalance, and symbol rate error. But again, these are what we call systematic errors. I didn't talk about that in the VNA section, but systematic errors are things that are predictable, that are always the same all the time. So if something's changing over time, obviously I can't compensate for that. Okay. So here's what some of these things look like. So if you see a QPSK signal here, so this is a QPSK signal, you see how these, instead of seeing 4 dots, they're kind of almost like rotated a little bit. So it's like a rotational error. That's my dance move for this afternoon. So, so the little rotational aspect of that. So that's from phase noise, right? Because the phase noise of the LO internally of my receiver is adding that rotational error to it. Okay, and if you look at a larger constellation, so this is what, 16 QAM. So you can see here, the more points I get, obviously the more and more critical that gets to deal with these noise errors. And I don't think I have a plot in here. Maybe I'll find it later. But for guys who do DOCSIS, so that's cable over or internet over cable, high throughput bidirectional data, they have a 16K QAM signal, right? So it's not over the air, it's through a cable, but still, think about that. That's crazy, right? The constellation's like stupid. So anyways, you can, but it just looks like a blob. So you have to look at kind of more the overall metrics, But yeah, I always like showing people that. It's pretty cool. Okay, thermal noise. So you see here, in this case, all the constellation points are sort of evenly too big. So they're too big in every direction. So, so that's what it would look like if you were more a thermal noise kind of thing. So this, you might see this in wide bandwidth signals, because obviously there's more noise in addition to more symbol signals over bandwidth. Yeah, so wider bandwidth by definition means there's more thermal noise. Okay, so another one, frequency response. So if you looked at the frequency response, you can see here the amplitude output is different over the entire frequency range. So you can see here you're getting these constellation points. They're noisy and they're actually, they look a little bit rotated. And here you see the EVM is 5.52. So I can turn on equalization and you could see those go away. So that looks like noisy. And I went from an EVM of 5.5 to an EVM of 0.29. So in this case, I know that I have a frequency response error, and I can fix it with the equalizer, but it's telling me in terms of my design of my system, that's the thing I need to focus on. Okay, so this is really kind of where everything's gone now, OFDM. Yeah.
So how did the instrument include this? Does it just measure across the
Yes, it's actually sampling that, it's measuring it, and then it's making its own equalizer internally in the instrument.
Does it take the median value, the middle, the average value? Which value does it take?
Well, I mean, when you do an equalizer, you're basically saying, like, I look at that response in totality, right? And then I'm going to want to more or less find the inverse of it to make it flat. Right? So I'm going to equalize it by putting a thing, instead of going down, it's going to go up, so it's going to make that look flat. Yeah. Okay. So that was all single carrier modulation. So basically that means not OFDM. So OFDM, what OFDM is doing, it's basically saying instead of one carrier, and we talked a lot about carriers, I'm going to take that signal and put it on a whole bunch of different carriers, right, together. And I'll explain why we do that in a sec. So when you modulate a signal carrier or a pair of carriers, we get a single bandwidth dependent on symbol rate, right? We talked about that. OFDM is orthogonal frequency division multiplexing. That's a mouthful. I can't believe I said that without. Anyways, so what OFDM does is it basically takes lots and lots of carriers and puts them really close together, okay, with really low symbol rates. But the key thing is it picks some of these frequencies and characteristics of these signals so that they cannot interfere with each other. They're orthogonal, right? So the point is, once I've modulated and all that, they should be completely independent. And so just like when I do the I and Q, right, those signals are in quadrature. So when I put the data together in that IQ stream, the I and the Q can't interfere with each other because they're in quadrature to each other. So this is trying to take advantage of that, but in more dimensions. So the other things with this is if I have lots of carriers and maybe I have a lower data rate or lower symbol rate in each one, I can have slower signals, right? So I'm more apt to not get errors. I'm not going to get multipath errors, things like that. So if you remember going way back, that when I'm moving around, the signal levels are changing very rapidly. Obviously, because my environment is changing rapidly, the reflections and whatnot, if my things come out, if my signals are coming out slowly or more slowly, I care less about that variation, right? If that makes sense. You had a question?
Do you need a different oscillator for each and every one of these carriers?
No. Yeah, you're going to basically take one and you're going to do some manipulation, just like we did on the IQ scheme, where I took one and I put it in quadrature.
But that's shifting phase by 90 degrees.
Right.
This is doing a different frequency, right?
Yes. But so I can do a lot of that digitally, right? So I can put an offset frequency into my baseband signal. I put an offset frequency into it. There's different means of doing it, but it's a good question. I'm sorry? 5G is, well, it's not really finalized yet. It's something close to this, OFDM. Yeah. No, because the thing about 5G, and I don't really want to get into a 5G discussion. I'm not an expert. Well, that's one of the variants, but realize like the whole thing with all of the more modern standards, like whether it's 5G or LTE, the whole thing is supposed to be variable, right? It's going to go and look at the channel. So we talk about channel estimation, and we talked about a lot of these other characteristics. It's going to go and try to send a 256 QAM signal over this channel, and it's going to say, you know what, I can't receive it. So guess what? I'm going to try a slower one, right? So it's going to do some analysis of the channel, and determine what's the best thing for that particular channel. And a lot of these things in terms of the carriers and the OFDM, these are all variables that they can use, whether it's the receiver or maybe the cell carrier might say, well, in this situation, I want to use this many carriers or this spacing or whatever. It's made to be more flexible to be able to do more different things, right? Okay, so, if you look at the spectrum, so this is a QPSK signal, 20 megasymbols per second, and this is a Wi-Fi signal. This wasn't a very helpful slide because it didn't tell me the characteristics of how many carriers and all that. But the point being was that they look very similar, right? So if I take a QPSK signal, this thing looks very similar. This is a slightly different shape at the top, but you can see they look very similar in terms of the spectrum. Okay, so OFDM is a whole nother conversation. I'm nowhere near an expert in OFDM. I've done some talks on it, but that's definitely where things are going. And processing it, it's not simply a VSA tool. It's really something that's designed to measure OFDM type signals. Normal VSA is saying I'm expecting one carrier. It's sort of beyond the scope of this discussion, but. Okay, so we started out talking about frequency spectrum, basic units, theorems, whatever. I bored you to sleep in the beginning there. And then we continued by talking about propagation, spectrum, how do we use components and how are they manipulated in systems. And then we finished by discussing how to model signals in the spectrum and how to design signals to transmit information. So, thank you.
That was great. Thank you, Neil, for presenting today and for the very informative RF Fundamentals webinar series. Now it's time for questions. So if you have any questions, please enter them into the Q&A section in the right side of your WebEx dashboard. In the meantime, I'd like to say thank you to all of our attendees today who made the time to sit with us on this webinar and for all of your participation. As I mentioned at the beginning of the webinar, it is being recorded and we'll send out an email with the recording in the next day. We have a new lineup of webinars coming up on our TestForce Academy. You can visit testforce.com/academy for more info. And we're always open to hearing your suggestions as well. So stay tuned for more invites and reach out if you'd like to. Okay, well, we did have a few questions come into the Q&A section, and we'll be getting back to you by email since they're much more specific in nature. If any other questions come up later, then don't hesitate to reply to my email or send a message to marketing@testforce.com, and we'll get back to you with all the answers. We've come to the end of the session today, but I look forward to hearing from you all and hope that you have a great day. Thanks again. Take care.